As we continue to work on Chapter 14 on acids and bases, we're going to get into increasingly more complex topics. And for example, today what we're going to do on this podcast is discuss what is Ka and how you can use it to calculate the pH of a weak acid, or if given pH, how to calculate the Ka. So what you see here is a generalized acid dissociation reaction. And anytime you see this, HA, that's referring to a generalized formula for a weak acid. And it'll actually react with the water. Notice the water is on the left as a reactant and form ions. And so we call this ionization. It says acid dissociation, but it really reacts with the water. So I'm going to call that ionization. And as you can see, it's a reversible reaction, so you can write an equilibrium expression for it, which says, and sometimes again, instead of hydronium, they'll have a hydrogen ion here. But the hydronium times the base, that's the A with a little minus, the conjugate base of the acid, over the original weak acid concentration is equal to its equilibrium constant. Of course, we emit water because it's a liquid. Now, you can create a number from this, specifically for weak acids, called Ka, the acid dissociation constant. And as you can see over here on the far right, they're pretty small numbers. These are acids that start to ionize and react with the water, but then reach equilibrium relatively quickly before very many products on the right-hand side are produced. And even though they can be quite complex, looking over at the left-hand column, you can see that they all have a hydrogen ion ready and available to donate. So the magnitude of the Ka indicates its strength. They're all negative exponents, something times 10 to the negative whatever. So the smaller the negative exponent gets, the greater the strength of that weaker acid. None of these are strong acids at all. You cannot use a Ka for a strong acid because those do completely dissociate. But weak acids only slightly ionize, and you can rank them with this unitless number called the Ka. So if someone gives you the pH, you can actually calculate the Ka. We're going to go back to using ICE charts, initial change equilibrium charts, that we learned from the chapter on equilibrium. So this is formic acid, used by a certain bunch of ants in communication and defense, the formicida ants. Really simple organic acid, and its pH of a 0.1 molar solution at a specified temperature, 25, was given, 2.38. Calculate the Ka. You should have an automatic reaction on any kind of Ka problem. I need you to write the equilibrium expression, absolutely, and writing the equilibrium expression implies that you know how to write the equation. So you would have started with acetic acid on the left-hand side, showing it reacting with water to produce hydronium ions and the formate ion, COO with the minus sign. So here will be in just a moment the ICE chart where we can show how to calculate the equilibrium concentrations given this, how to calculate the Ka given the pH, which you get from equilibrium concentrations. So let's take a look at the actual chart here. We're going to need to go from pH into hydronium ion concentration so we can find the equilibrium concentrations of the acid. And that's pretty simple to do. You just take 10 to the negative pH. We're doing something called an antilog. So 10 to the, make sure you make the pH negative, 10 to the negative 2.38 will equal the hydronium ion. So when you punch that into your calculator, you get a fairly small number, 4.2 times 10 to the minus 3. Since hydronium and formate ion, that's this guy, the HCOO minus, are in a 1-to-1 ratio in the equation, then whatever the concentration of the hydronium is the same as that of its formate, the conjugate base. So now we have a nice chart. Now in my opinion, I would have set up the equation first, and notice that they've just put at the top of the chart the concentrations. I would have actually have an arrow drawn right here, and I would have shown on the left-hand side water reacting with the formic acid, but that's your call. We always ignore the water in the end anyways. So they had given us an initial concentration, but from pH, you had calculated the final concentration of hydronium and then by stoichiometry predicted the final concentration of the formate. So while this chart fills in vertically from top to bottom, I would have placed the number 4.2 times 10 to the minus 3 molar at the bottom in the columns for hydronium and for the formate ion here. So once you know that that was the equilibrium concentration, if you start with 0 of the hydronium and formate, because if you just plunk the acid into the water, at the moment right before you put it in, there are no hydronium or formate ions, then if that is their final concentration, that must have been also their change, plus 4.2 times 10 to the negative 3. If this gained in concentration by that amount, then the original formic acid must have lost in the original, from that original amount in the same value. So that's why there's a minus 4.2 times 10 to the minus 3. Now as you can see, when you actually take 0.1 and subtract 4.2 times 10 to the minus 3 molar from it, you get a pretty tiny number, which they, brazenly put as 0.1. I'll talk to you in a little bit about how you can make these kind of assumptions. But essentially the concentration in this problem of the formic acid is changing very little. You could have left it in as 0.0958, but it won't make a difference in your final answer. So now we have the equilibrium concentrations, and all you need to do is to punch those into the original expression for Ka and then solve. So what's nice about a lot of these Ka problems, if they're in a 1-to-1 ratio, is that you can simply square the equilibrium concentrations of the acid and the conjugate base, in this case hydronium and formate ion, and then hit divide by the original concentration. Now I just want to point out that this Ka is one of the larger Kas, 1.8 times 10 to the minus 4 molar, or actually 1.8 times 10 to the minus 4, the Ks are a unitless number. But what I'm trying to point out is that sometimes as the strength of the weak acid gets stronger, then you might not be able to make the kinds of assumptions that we'll be doing in these first problems, and I'll come back to that later. In addition to calculating Ka from pH, and by the way, the problem we just went through on the PowerPoint is sample exercise 16.10, shown in its full glory here. So if you'd like to look at it in the textbook again, or look at it again from a different perspective than the PowerPoint, feel free to do so. As I started to say, in addition to being able to calculate Ka from pH, there's a concept with acids and bases that's called percent ionization. And this goes to the concept that I've sort of been simplifying in the past. We talked about covalent compounds. We talked about ionic compounds, and sometimes you can get substances that are kind of in between, and acids sort of fall into that, at least weak acids fall into that category. So when, let's see, in this case it looks like we have acetic acid here. When you want to calculate percent ionization, you're looking at how much of the original acid on a percentage base turns into ions. And the greater you go towards 100% makes things more like ionic. And as you go towards the other direction where they're not ionizing very much, makes them sort of covalent. Well, acids are interesting because they're kind of in between the sort of molecular covalent nature and the ionic nature. So let's go ahead and take a look though how easy it is to calculate something called percent ionization. Let me back up and check that I haven't forgotten some data. Okay, this will be sample exercise 16.1 in the textbook. And in this particular example, someone will tell you that the hydronium ion concentration is 4.2 times 10 to the minus 3. And the original, oh, sorry, this is the same problem, I guess, from before. The original concentration of that formic acid was 0.1. So if you have the amount that forms as ions divided by the original amount in concentration and molarity and times it by 100, you can quickly find that the calculation of percent ionization is pretty simple. And because it was 0.1 molar and you have 4.2 times 10 to the minus 3, it only ionized 4.2%. What that means is that 95.8% of the original formic acid is still swimming around in the water undissociated. Remember, it's an equilibrium. It'll keep ionizing, and then ions bump into each other and go back to form the molecular substance again. But most of what you would see is unreacted formic acid in that ionic soup. So percent ionization is kind of a simple calculation, but we calculated that original, the hydronium ion concentration from using the original value of pH. So hopefully you're comfortable with pH problems now. And this is that same problem again. 16.11 will be the sample exercise that corresponds to percent ionization if you would like to check the textbook. I'll do one last problem and stop this segment. If someone gives you the Ka, you can also use an ice chart to calculate the pH. Here is the correct equation that's written, and hopefully you've been conditioned to understand that if you are given acetic acid, a weak acid, to immediately write the expression and write a Ka expression for it. You would either look up or be given a Ka, and there's a table in the back of the textbook with common Kas for common weak acids. So here is our expression, and the thing that we know is the Ka. What we don't know are the equilibrium concentrations of hydronium, acetate, and acetic acid. So here is the ice table, and again I prefer that you would write acetic acid, which they've written, I think, incorrectly. That looks like a typo to me. Yeah, there seems to be something missing, like the hydrogen ion here. But let's pretend that said acetic acid. I would have drawn plus water, drawn an arrow, shown the hydronium plus the acetate ion. I don't know what these guys were doing. So all we know is the initial concentration. So we learned about the let X equal method back when we studied equilibrium chapter in the fall. So the change would be that the acetic acid would lose X amount of concentration, and therefore, since the stoichiometry is 1 to 1 to 1, the hydronium and the acetate ion concentration would increase by a value of X. So at equilibrium, that would be my equilibrium concentrations, and they've made the assumption, because the Ka given was pretty small, you'll memorize the Ka for acetic acid after a while, because it's something times 10 to the minus 5, you can essentially assume that the acetic acid concentration doesn't change. So you set your Ka given, 1.8 times 10 to the minus 5, equals x squared over 0.3. And when you're done solving for X, you're still not done. X will be the concentration of the hydronium ion, and it is from that that you will take the negative log of that value. And that is how you would calculate that the pH would be 2.64. So Ka is a useful value. It allows you to take a Ka value and an expression and calculate pH. Or if given pH, you can go the reverse direction and calculate Ka. Here is another problem in the textbook, which I would like for you to take a moment to copy into your PowerPoint notes. This one is using hydrocyanic acid. Notice it says to refer to a table or an appendix to get the value of the Ka. And I'd just like to point out, when the Ka is very small, times 10 to the negative 10, you always get to ignore the X in terms of change of the original acid concentration. So these problems become very simple. X squared divided by 0.2 will be equal to the given Ka, and you can solve for X, and from that take the negative log. So here we are solving for the X value, and then take the negative log of that number to get the pH. And that makes sense, because if you look at the, well, let me back up. no, I think that's a good spot to stop there. Okay, so notice that using that approximation is a safe bet when the Ka is so small. I believe I will stop there and pick up how to calculate percent ionization from Ka at the next podcast.